Hello everybody. As we are moving through chapter 19, I'd like to point out that the next few segments are very heavy in mechanistic understanding. So let's just get a start of this. This chapter begins with basically highlighting the different types of mechanism modes that are possible. So section 19.4 is focusing on nucleophilic addition reactions to the carbonyl group. What we want to realize is that the carbonyl carbon is electrophilic. We can also describe this by saying that there's a delta plus here on the carbon and a delta minus over here on the oxygen. There are two possible resonance forms that you should be very familiar with now. And when we look at the overall induction, basically we're thinking about delta plus on carbon, delta minus on the oxygen. That already sets us up for two modes of reactions. The carbonyl group in aldehydes and ketones can both be electrophilic and nucleophilic. Electrophilic on the carbon, nucleophilic on the oxygen. And as we see in this depiction here, the nucleophilicity can either come by moving the double bond or using the electron pair. On the next slide, here we see that basically aldehydes are typically more reactive towards nucleophiles than ketones. There are two aspects to this. Sterics, which means bulkiness. Aldehydes are less sterically hindered, which means that basically we're comparing a hydrogen, a small atom, versus an alkyl group. This is smaller, making this position more readily available for nucleophilic attack. And then there are electronic effects. So the aldehyde has a larger delta plus. Delta plus, it's sort of like, it's a proportional kind of labeling. We show where there are partial positive, partial negative charges. They're very different from formal charges. So the aldehyde has a larger partial positive charge on the carbonyl carbon. Here we see the ketone, 2 electron donating alkyl groups that stabilize the partial positive charge. Remember, this is an inductive effect. Inductive effects are smaller than resonance effects, but nonetheless, here we have alkyl groups with more electron density than just sort of the smallest atom, the hydrogen. So that is going to make a big difference. On this slide here, we're now discussing, or beginning to discuss, two major mechanistic approaches. We need to recognize that the reactions in this chapter depend on the acidic medium or the basic medium that is given. So we have to recognize what it means. We're going to start out with basic conditions. All nucleophiles react with carbonyls by the same general mechanism. Here we have the outline. The carbonyl group, make sure you draw the free electron pairs. The nucleophile, in this case, it's a strong nucleophile. It not only has an electron pair to donate, but also negative charge. We then form an intermediate. This is called a tetrahedral intermediate. It's also highlighted down here. And then in the second step, we have the oxygen with a negative charge picking up the proton to then come up with this intermediate over here. So, two-step process, nucleophilic attack, proton transfer. The carbonyl carbon is attacked by nucleophiles, forming a new sigma bond, right? We're going from 2 single bonds and a pi bond to now 4 single bonds. So we've basically created a new sigma bond, a new single bond. Nucleophilic attack, forming a negatively charged intermediate, which is protonate upon acidic workup. So here we have it. Our carbonyl compound, and this applies to both aldehydes or ketones. This is planar, trigonal planar, because this carbon over here is sp2 hybridized. When the nucleophile attacks, in this case it's a strong nucleophile, Why? Because it has a free electron pair, has negative charge. It can attack either from the top face or the bottom face. And then we observe this tetrahedral intermediate. That's a really important component. Tetrahedral meaning that it wants to be close to 109 degrees all around for the 4 single bonds. We see now the nucleophile has been introduced. Here's our negative charge. And all that is missing, basically protonation, also referred to acidic workup. So we look for conditions that introduce an H+, and then basically you will get your hydrogen attached to the oxygen, and then it looks like this. As we move on, basic conditions, and I've kind of inserted here that if this is a concept that is difficult to you, you may want to look back into chapter 3, which discusses acid-base chemistry, just as a refresher or maybe some clarification, so that you can succeed in learning the new material where acid-base chemistry is going to play some role. In general, a strong nucleophile means that the reactions under basic conditions, and there are 2 examples, Grignards and Hydrides. I'm going to put in the Grignards here. Here's a carbonyl group, ketone or aldehyde. This is a 2-step procedure. The first one, this one is the Grignard reagent. And I would encourage you to think about this as we have an alkyl group, such as a methyl group. We have magnesium in here. And then we have a bond to a halide, such as the bromine over here. This Grignard reagent is actually derived from a halide. So in this case, it would be methyl bromide. And the conditions necessary to make the Grignard reagent would be using magnesium. I'm going to switch colors here. As you know from the many reactions for substitution reactions in Orgo 1, when we have an alkyl group and a halide, that the polarization is going to be delta plus and delta minus. However, when we are introducing magnesium, a metal from main group number 4, it basically will insert into the carbon-bromine bond, and that is shown here. I've used the abbreviation for methyl. So it's a carbon-magnesium-bromine bond. And there's a significant difference to this now. Magnesium from main group number 2 is going to be delta positive. The halide will be delta negative. And now, surprisingly, and it's a bit unusual, but the carbon with the 3 hydrogens is going to be delta negative. In other words, we have reversed the delta positive, and now we're dealing with the delta negative. In German, it's also known as Umpolung, which is sometimes mentioned in some of the textbooks, because we're just changing the electronics. So instead of this being an electrophilic position for like an SN2 reaction, we're now dealing with a delta negative where this R group is going to be a very powerful nucleophile. And then we say that this has to do with basic conditions. So we can think of a Grignard reagent as follows. When we have an R, Mg, and then we can use another placeholder, X, we can think of this as a source of a very unusual nucleophile. So here it would mean R dot dot minus. So it's a very powerful nucleophile. Okay, that's going to attack in the electrophilic position carbon here. It's going to open up the double bond to form that intermediate we've seen before. Step 2 is quenching the reaction, converting this to an alcohol group, and here you are, going from sp2 to sp3. A simple example, and I want to remind you to your chapter 12 that dealt with alcohols. Basically, we can do similar reactions. If I'm going to use the simplest aldehyde, formaldehyde, here we are. There are 2 hydrogens, but we can use many other carbonyl compounds. Right now we're focused on aldehydes and ketones. When we are looking at a hydride reduction, basically it's a net delivery of H, and this is a bit unusual because usually we associate hydrogen with a positive charge in the form of a proton, but here we have now a delta minus, okay? So this is negative, this is very powerful, and maybe let me just clear that up a little bit. Let me so this is a negative charge. This electron pair will attack on the delta positive carbon. It's going to open up the double bond and form a negative charge on the oxygen, and then you're going to have, in the second step, essentially an acid workup that will have a source of proton. Okay, and then you're going to end up with basically an OH group here. I want to make sure I fill in the other hydrogens. And that is akin to a reduction reaction, okay? So that's some of the simplest cases that we can encounter for nucleophilic attack. On this slide here, we see aldehydes, ketones react with a variety of weaker nucleophiles. And we can accomplish this and speed up the reaction by using acidic conditions. What's the bottom line here? So this is type 2 mechanism, 19.2, nucleophilic addition under acidic conditions. Okay, so acid-base chemistry, we need to apply our knowledge. In this case, we're basically reversing the order. We do a proton transfer first and then a nucleophilic attack. Proton transfer first means that the nucleophilic portion of this oxygen here with a free electron pair is going to pick up a proton. So this is a net H plus transfer, right? As it says up here, proton transfer. We have now activated that carbonyl group so that even weaker nucleophiles can attack. Weaker nucleophiles means that it could be an NUC ... minus, but frankly, it could also be an NUC that only has a ... and no formal charge, okay? And that's going to lead us to the same tetrahedral intermediate in this. So, carbonyl group is protonated to form this positively charged intermediate, which can be attacked by a weaker nucleophile, something that may not have a full formal negative charge. Next slide. We're looking in more detail. Acidic conditions are required to really make it easier for the carbonyl group to be attacked. And here you have it again. This is just a generic placeholder, HA, and you're going to form an oxygen with 3 bonds and a negative and a positive charge. Pardon me, positive charge here, and there's an equilibrium. This is actually a resonance form where we can then look at the positive charge being moved onto the carbon atom. So, protonation, meaning addition of H plus H plus, makes the carbon a bit electrophile and activates it for a nucleophilic attack. So, when the nucleophile attacks the carbonyl group, equilibrium depends on the ability of the nucleophile to function as a leaving group. One example here is when we have a carbonyl group, an aldehyde or a ketone reacting with HCl. Remember that HCl is going to be in equilibrium with H plus and Cl minus. And we can look at where the equilibrium lies in here. Cl minus, chlorine in main group number 7 likes to attract more electrons. It can act as a nucleophile, as we have seen in many substitution reactions in Orgo-1. And basically, it's a net addition of a hydrogen and a chlorine. The hydrogen ends up with the oxygen, and the chlorine on the carbon atom. And so you can further examine this equilibrium, and there are other aspects to this. So the nucleophile Cl minus is also a good leaving group, and that kind of sometimes makes it difficult to understand the role it might play. On the next slide, basically, as we're looking at the carbonyl groups of aldehydes and ketones, they can react with really many different nucleophiles. And in the boxed area here, we see that water, which is not a strong nucleophile, can actually form a hydrate. There are certain factors that influence where the equilibrium lies and how readily the hydrate is formed. But basically what we need to recognize is that, because, remember how we started out, there's a delta plus on the carbon and a delta minus on the oxygen. There's very rich chemistry here that we need to contemplate. In order to understand a nucleophile attacking the delta plus carbon here, we can now analyze a whole host of different potential nucleophiles. So oxygen, we only need one of the electron pairs on the water molecules. We can say the same thing of the alcohol. We can even have reactions with diols, as shown here. I'm just filling in all the electron pairs that, and one of them is going to be necessary to launch a nucleophilic attack. So as I'm filling this in, these are common bonding patterns, and these electrons do play a role in the reactivity of all the molecules. So nitrogen, we have one electron pair. This one is a primary, this one is a primary amine. There's only one alkyl group. This one is a secondary amine. There are two alkyl groups. This is going to play an important role in the next segment. Then we have much stronger nucleophiles where hydrogen and carbon are going to play a key role. LAH, also known as lithium aluminum hydride. It's a hydride. And then here we have borohydride. Here the counter ion is Li plus lithium. What would it be here? This is typically Na plus sodium borohydride, which you encountered in Orgo-1. So these are all sources of a hydride, H dot and minus, okay? And we just had discussed, let me just undo this. I want to get the circle around better. So hydride, this is the key component for the reaction that we want to consider. And then there are a number of carbon nucleophiles, Grignard. We actually just looked at the dynamics or the electronic situation of this. Nitrile, that's a good nucleophile, as you know from substitution reactions in Orgo-1. And here is a reagent, a phosphorus reagent, very important in a Vidic reaction. So this is a named reaction named after a famous chemist who has made pivotal progress in synthesis, because he realized that these phosphorus reagents, and I'm going to abbreviate this, are very potent nucleophiles. Here's the negative charge. That's going to start the reaction. This textbook proposes or emphasizes the 2+2 cycloaddition reaction, but basically you can think of the reaction starting with this negative charge, this free electron pair attacking the carbonyl group over here. And I also want you to understand that in a Wittig reaction, we can draw another resonance form. So we use the resonance arrow. Here it is. And instead of having an Illich structure, which means that a positive and a negative charge are right next to each other, we are dealing with now, here's the resonance form. There can be a double bond character between the phosphorus and the carbon. On the next slide, as I said before, practicing these skills will be very helpful. In this case, I'm going to help you start out the practice problem. You can look it up. You even have the solutions manual where you can look up the answers to this. Here under 19.6, we have a carbonyl group, a cyclohexanone, with a Grignard reagent that gives you this product. So the carbonyl group is converted to a hydroxyl group, and we have an ethyl group, ET, and this is this right here. Okay. Now, here it asks you to draw a mechanism. So what are the conditions? Are they basic? Are they acidic? We know that Grignard means basic conditions first. You will have essentially an ethyl dot minus as a nucleophile. It's going to attack delta positive of the carbonyl group, and then you can work out your mechanism. In B, what are the conditions? This means acidic. So first you have to start out by making sure that you draw all your electrons. This is going to be protonated, which will make it easier for weaker nucleophiles to attack. And there you go. All right. So in this segment here, in the presence of water, a ketone or aldehyde is in equilibrium with its hydrate. Hydrate literally means addition of water. So we can think of this as, and this is not to describe a mechanism, but again, I'd like to visualize to maybe help you understand how bonds are made and broken. And basically, we are adding a molecule of hydrogen where a new bond is made between the carbon and the OH group, and then oxygen and the hydrogen. And there you are, you have your hydrate. The equilibrium generally does not favor the formation of the hydrate except for very simple aldehydes, but we can formulate a lot of different reactions here. Pardon me. The rate of reaction is slow unless we have acidic or basic conditions. So we might need to add some persuasion here by adding something else on the reaction arrow, but this is just a very general scheme here. Now, oxygen nucleophiles, when we look at basic conditions, it means that we have hydroxyl anion. So that's OH minus. Please note that basic conditions, we cannot tolerate acidic components in there. They will not exist. And I'll have another slide to actually address this. Here in this base catalyzed hydration, hydration means net addition of H2O. I've kind of showed it before, but this is the mechanism. The hydroxide anion is going to attack the delta positive carbon as you make a new bond. bond here. Carbon can only have 4 bonds, so this bond needs to be broken. We get to the tetrahedral intermediate, we get to another proton transfer reaction, and there you are, and you have your hydrate. Under acidic conditions, it means that we have a source of a proton. Proton is a net H+, and often what is shown is that this is associated with a water molecule, and so we're talking about an H3O+. And that H3O+ is actually what's shown in this mechanism. We're now using the oxygen side. One of the electron pairs, only one of them, is going to be able to attack the hydronium ion. It's a net proton transfer. We then have this structure over here. This now makes it more susceptible to a nucleophilic attack, even by a weak nucleophile, in this case a neutral water molecule. It's going to attack and break open this bond. We have a tetrahedral intermediate. At the same time, the water molecule has turned into this kind of bonding pattern. One of the electron pairs was used to make a new single bond, which is shown over here. And just a simple proton transfer reaction, meaning that this is a net proton loss by adding H2O and then getting rid of H3O plus, and here we get the hydrate. So as you practice with the conceptual checkpoint, just remember that we need to ask the question, is this like acidic, or basic? And again, you have a student study guide and solutions manual available as you're working with the in-chapter and end-of-chapter problems. So, just to emphasize again, acidic and basic conditions, that differentiation is really important for understanding the mechanisms that can happen. When you're drawing mechanisms under acidic conditions, let me just underline this, acidic conditions. So we have to avoid the use or formation of strong bases. A strong base cannot exist in an acidic environment. It's just not going to be there. Acidic means that you can use things like H+, H3O+, and water, but you cannot, under acidic conditions, have something like OH-, okay? So this will not exist. You cannot use this in any mechanism. Sometimes students think that, oh, it's going to save me a step because it quenches the charge, but this is really wrong. So we're going to cross this out, okay? Under basic conditions, the mechanism will only be reasonable if it avoids the use of formation of a strong acid. A strong acid cannot exist in a basic environment, okay? So as we're looking at this component now here, basic conditions. Basic conditions, what are the things we can use? We can use OH-. We can use a molecule of water. However, we cannot use in the mechanism any of the following. We cannot use H+, because we're in basic conditions. We cannot use H3O+, which is really H+ solvated. So we really have to be familiar with this, and we have to cross this out. So in our mechanistic details, we cannot use any of these. Okay. So Oxygen nucleophiles, alcohols can attack ketones and aldehydes. What do we need to recognize? Remember that basically we're adding, and it's kind of similar to the hydration reaction before. If we think about an alcohol molecule, we can add first an R, O, let me back up, I'm sorry, we can think of this as adding an alcohol, R, OH, across that double bond. So how do we think about this? You may want to pause. I mean, and I know that there are two molecules of ROH that are being introduced. But let's just start with the first one. How is this going to interact with this? Pause the video, think about it, jot something down. Okay. So as we are looking at our carbonyl group, we actually have to understand that this is a stepwise procedure. And the way I like to think about it is that if we are breaking up our reactant, and I made the parallel to our hydration reaction forming a hydrate. It's really very similar. But instead of H2O, we're now using ROH. HOH versus ROH. So, what do we do with this? We can see how first we actually need to form what is called a hemiacetal before we get to the acetal. Hemi means half. So we go from here to, we have an oxygen, carbon-oxygen bond. This hydrogen is going to end up over here. And then because the double bond has now been broken into two single bonds, we are now going to add OR. And this is your hemiacetal. And that in a sequence of steps, and I'm not counting here, this OH group is going to turn into an OR group. So it's a lot more complex, but I just want to point out and visualize the overall outcome. Under acidic conditions, one ketone or aldehyde reacts with two alcohols to form an acetal, which is shown here, and this is the hemiacetal. This reaction needs persuasion. It needs acid as a catalyst. Two possible reagents that can be used are para-toluene sulfonic acid, or TSOH. This is a delivery system for a proton, or sulfuric acid. So that's another possibility. All right, as we move on, in this slide here, you have the details. I recommend you pause. I'm not going to walk through everything in this. You have it in your textbook as well. You decide what you need to prioritize. Maybe you want to write down the first couple of steps to get you going. But it would be helpful for you to understand each step, especially when it comes to classification. Remember that organic chemistry is very much about pattern recognition. So here we are. The beginning is a proton transfer, oxygen, free electron pairs attacking the acid source. You form this intermediate, and then you go through a whole slew of different processes. On the next slide, we have acetal formation description, which is really, it's always an equilibrium. In this case, we can skew it in one way or the other. Basically, another way of looking at this is that a carbon-oxygen double bond is going to be replaced with two carbon-oxygen single bonds, in which the ethyl group over here is going to show up in the acetal. So that's for pattern recognition. Most ketones, the acetal is not formed at equilibrium, and that's expressed over here. So there can be some specifics. Aldehydes are more persuasive, as mentioned in the beginning. They're more reactive, and ketones can be more sluggish in their transformation. Over here, we now have a kind of different situation in which the carbonyl group is not treated with two molecules of an alcohol. Instead, we have a diol, but nonetheless, we have two OH groups that can be incorporated. First, we have the hemiacetal, as mentioned before. And then we're going to convert this into an acetal, which is going to be cyclic because the two alcohol groups are linked. Overall, there are 3 steps to get here and 4 steps to get here. It's good practice. And then also, you have skill builder 19.2. As you're looking at this, so here you have, instead of acetone, the cyclohexanone. We see that we are forming the acetal. And guess what? What are the conditions here? They're going to be acidic. There's going to be a loss of water, also known as a dehydration step overall, or a condensation reaction. And then here, whenever you see the training wheel, this is a great opportunity for you to pick one or maybe more to work through these to understand the foundational or the very important skills in this chapter. Here, acetal formation is reversible. We can actually take this to or use this to our advantage. Acetal formation can be favored when we are removing the water. Remember, this is a dehydration reaction, so there are certain actually equipment pieces where we can just draw out the water and then move the equilibrium from left to right. But at the same time, if we dilute this, we can get rid of this. And this basically becomes a way for protecting certain functionalities, carbonyl functionalities. So here's a ketone. We can protect also aldehydes, meaning that we put something here so it won't react. We can make other modifications. And then after we're done with the other modifications, we can just remove the protecting group. Okay. And then also hemiacetal is the intermediate that is formed, as I had said before. So we now see it broken down a little bit differently with color coding. First, one molecule of alcohol is added. Here's your hemiacetal. These may or may not be able to be isolated. In this equation, they're trying to maintain some balance. And we have another alcohol molecule here, which will essentially or effectively in the end replace the hydroxyl group. So that's when we come up with the acetal. And these can be isolated. And I had mentioned just at the beginning that in this chapter on ketones and aldehydes, we can apply a lot of the same chemistry to carbohydrates, meaning to molecules like glucose, fructose, and then various derivatives of this class. And on the next slide here, we see that a cyclic hemiacetal is also possible when a compound contains both the carbonyl group and the hydroxyl group. So here we are. We have the carbonyl group, and now we have an alcohol. So we're going to form something that is cyclic. We have acidic conditions. It's important to recognize that. Here it becomes important. I have to do this still after decades of working in organic chemistry. 1, 2, 3, 4, 5. Okay. This is the carbon with 2 bonds to oxygen. Where's the carbon with 2 bonds to oxygen? It's right here. Okay. So if I wanted to label this, I'm going to put a dot here and a dot here. Okay. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All the carbons are there. Here we have the oxygen, the OH group. We can find that over here. But essentially, we are converting a carbon-oxygen double bond to 2 carbon-oxygen single bonds. So that can help us guide. And as I just had mentioned, cyclic hemiacetals are important in carbohydrate chemistry. So this is going to be a preview to chapter 24 when we talk about carbohydrates. We have both a carbonyl group and a hydroxyl group in here. And it turns out that glucose, fructose, dimers, polymers of carbohydrates, carbohydrate quote-unquote monomers, we can actually have ring structures. Glucose is a cyclic hemiacetal. The carbon-oxygen double bond here has become 2 carbon-oxygen single bonds. And that's going to be really important to understand that aspect as later in the semester. So we still will cover a lot of other material until we get to carbohydrates.